Special triangles are the triangles that come from our first two perfectly symmetrical shapes. And those shapes are the equilateral triangle, okay, which is a 60-60-60 triangle, and all the sides are the same length, and the square, which has 90 degrees in each corner, and each length is the same length. Sorry, each side is the same length. So these are special because we don't need any technology to help us out with these, because we can split these right down the middle. Okay, we can symmetrically divide these into two equal parts. And so when we do this, we know all the parts of this triangle without having to rely on technology. And our technology helped us go from angle to ratio and ratio to angle. Well, we know that the ratio of side lengths of this equilateral triangle is 1 to 1 to 1, or in this case the way I've drawn it is 2 to 2. And we know the angles are 60, 60, 60 in those corners. We didn't need our calculators to do that. So what we can then do is we can generate our right triangle by splitting this straight down the middle. And because we did it symmetrically straight down the middle, we know that this angle is 30 degrees. And using Pythagoras, we can find this third side. And we don't need anything to translate between this ratio description of the triangle to the angle description of this triangle. So this 30, 60, 90 triangle is what we call a special triangle, and you're expected to be able to do problems on these triangles without using a calculator. Same here, we have our square. This is going to be 1 to 1 to 1 to 1. And we know that this is a perfectly symmetrical shape, so we can split it right down the middle along this diagonal. And we know when we do that, we're going to generate this 45 degree and 45 degree triangle. So these being isosceles, okay, we know that they're the same length. They generate 45 degrees. We don't need a calculator to tell us that this ratio of 1 to 1 gives us a 45 degree triangle. And using Pythagoras, we can find the third side here of root 2. So we know that any triangle with these ratios, we know that this is a 45 degree triangle without having to rely on our calculator to find that for us. So how do we use these triangles to solve problems without using a calculator? Well, here I have a 60 degree angle here on a 90 degree triangle. Well, this must mean that the top angle is 30 degrees, and this shape again should be familiar to us. This is a 30-60 triangle. And what we know about this is that the sine of 60 is going to be this side, or root 3 to 2. The cosine of 60 degrees is going to be 1 to 2. And the tan is going to be root 3 to 1. So we know all the ratios without having to go to a calculator to find the ratio from 60 degrees. So we can solve this in many different ways. We can just solve this as similar triangles. That's probably the easiest way to do it. I am going to relate this to some trig ratios to make this more consistent with what we've been doing. But if I want to solve for x, I want to use this side opposite of 60 and the hypotenuse. Okay, so I have opposite and hypotenuse. Well, opposite and hypotenuse is sine. So I know that this is going to be sine of 60 degrees. Okay, and the sine of 60 degrees I may not be as familiar with, but I'm familiar with this triangle, and I know it's going to be root 3 to 2. Okay, and if you're not familiar with these triangles, you're going to have to get familiar with these, because these are going to have to be known triangles. Okay, these become things that are known information, and we could always figure them out, but you should know these as we're doing it. So if I look at the opposite to hypotenuse ratio on the known triangle, it's going to be root 3 to 2. And I can solve this, and so sine 60 is equal to root 3 over 2. I didn't use my calculator. Notice I didn't get a decimal value. If I went to my calculator and got a decimal value, I'd get 0.866. That's not something that we're going to use. We're not going to use the decimal values for these, because these are known triangles. We can work these out using symmetry, which is math, so we're not going to rely on some technology to do this. So then going ahead and solving for x, I'm going to just solve this algebraically. For x, I'm going to rewrite this equation. Okay, I can cross multiply this or solve this algebraically, times both sides by 5. So I get 5 over root 3. So this length here is going to be 5 root 3 over 2. And that length is approximately, if I'm not mistaken, about 4.8. Okay, so 5 root 3 divided by 2 is 4.33. Okay, so this is approximately 4.33. Okay, the solution we want to give is this one. Okay, I will accept decimal solutions, but really what we want is we want the exact value solution. And when we're dealing with these specifically special triangles, you're going to have to keep your answers in exact values. So then solving for the y is pretty easy if I think of this in terms of similar triangles. I know that y is exactly half the length. The bottom side here, the adjacent side, is half the length of the hypotenuse. I can see my hypotenuse is 2, my adjacent is 1. So I know my y value is equal to 2.5. But again, I want to use a trig ratio. Okay, and again, you don't really have to, but I'm going to use a trig ratio, adjacent side of y to the hypotenuse. Okay, so katoa, that's going to be my ka. So adjacent is going to be 1. Cosine of 60 degrees, I can't write that. My cosine has to equal adjacent compared to the hypotenuse. Okay, so I'd rewrite my equation, y over 5 is equal to 1 to 2. Solving it as a proportion, I get 2.5. I can solve this algebraically. Again, it doesn't really matter how I do this. Okay, 2.5 is an exact decimal. That's perfectly okay to leave it as a decimal. However, let's try to get in the habit of using fractions.